Hello, YouTube. This is Luis back for CS 4540, and this week's topic will once again be talking about LLMs, but we'll also be explaining a little more about attention in transformers. For this week's discussion, I will be mainly talking about uh, one video, uh, and that video spans about an hour long, titled Visualizing Transformers and Attention, guided by the channel 3 Blue 1 Brown. And we continue with the premise of an idea of a text prediction model that takes in an input and assigns a probability distribution to all possible next words. And the hope is with this foundation, you can turn it into something that will generate new text simply by having it randomly grab from that probability distribution and repeating that process. In last week's video, we also touched on tokens, which we describe as being inputs broken into chunks, and each chunk being given a value based on a predefined vocabulary of all possible tokens. These values are given by its embedding as a vector made up of many, different values. And we pass this through an attention block, which will be the focus of the video later on. But basically, this block allows these vectors to exchange information back and forth so that a word that would have started being encoded by its more literal definition in the vocabulary uh, to later have some of its context also taken into account. Now, these vectors don't just go through one attention block, but rather flow through many iterations in this attention block, as well as something called a multi-layer perceptron, which holds the majority of the model's parameters. And at the end of this process, you want to look at that last vector in the sequence, which will, in the video was the word was in the input phrase to date, the cleverest thinker of all time was, right? And, this vector will end up holding much more meaning uh, given its context. And through this context is able to make a prediction for what might come next. And now we get into the topic of the attention block and what exactly goes on inside of that. Um, what goes on inside that allows these vectors or these tokens to interact and transfer information between one another? These token vectors not only encode the literal meaning or value of that token, but also encode its positioning in the input. And this is important because by holding its position value in the vector, we can have it so that these vectors can remain parallelizable, meaning all their necessary computations can be done independently of one another. Um, and not having to rely on the order that they're done in. Um, you don't want the meaning to be inferred from the way the data is processed, but rather from the state of the token itself. And this brings us to the helpful design choice of this process, that being to make sure that the operations we're working with can be expressed in the language of matrix multiplication. The video actually states this pretty well with the quote, how can I express this notion of letting one thing influence another using only the language of multiplying matrices together, where those matrices have tunable weights in them that can learn what we want them to? And there are three matrices that are going to come up in this discussion that I want you to keep an eye on. Those being the query, the key, and the value matrices. The query matrix takes an individual token and checks the context of its position in the input and any valuable information of the surrounding tokens. These positions are embedded in a new vector called the query vector, and it's associated with that token made by multiplying with the query matrix. And the hope is that the resulting matrix will be able to pick up the token's embedding. Or if the token's embedding is, like, for instance, a noun, then it should be looking for adjectives in certain positions in the input. And you follow this logic, this process, with every token in the input statement, multiplying each matrix with the larger query matrix. However, at the same time these query vectors are produced, you multiply them by a distinct key matrix made up of a sequence of key vectors, the ones on the left. And the idea for these keys is to hold information about its associated token, so that when a query matrix is looking through the input for a particular token, that key matrix will be there to answer and let these matrices interact with one another. For instance, you might have a noun, and its query matrix, picking up on the fact that it's a noun, will be searching for adjectives in the input. And so the keys associated with those adjective tokens will then be able to respond and provide the information of where the adjective tokens are and provide the context for that noun token. And the way this is presented in something like a multidimensional space is that these query vectors will be pointing in the same direction, such that the adjectives or verbs about the same noun will be grouped together and pointing in similar directions. To be more specific, the relation between these vectors is found with the dot product for every pairing of query and key vectors, showing which words or tokens are relevant to updating the meaning of other words or tokens. In the example from the video with adjectives and nouns, adjective words like fluffy and blue, when paired with their corresponding noun, which in this case is creature, produce a higher dot product that signals their relation to one another. And this relation has a term for it described in the video as attend to. These tokens attend to this token. Fluffy and blue attend to creature. Yeah. And we want to take a weighted sum according to how much each vector on the left attends to the one on the top, right? Where we want the bigger ones to matter more and the smaller ones to matter less. And for these to act like weights, we pass them through something called softmax, which is an exponential function that takes in everything and normalizes them. By when outputting values through softmaxing, you get a value between 0 and 1. And the larger of these values will correspond to larger probabilities. And what makes this process softmaxing is that you can continuously develop these parameters so as to get a smoother change similar to that of gradient descent. You pass each vector, every column in this query and key vector pairing diagram, through the softmax function to get a sense of which weights for which words are going to be relevant to updating the words at the top. And this is what we call an attention pattern. We then get into the topic of how exactly embeddings for words talk to each other so as to influence and update themselves to point in a more specific direction. We achieve this by using another matrix called the value matrix, where we multiply with a given token vector and the resulting value produces a new vector that, when added onto the embedding of another vector, uh, it will point that vector in a more specific direction that encodes whatever reference context is needed uh, for that original vector. And I actually touch on this in last week's video, but essentially, as you add more context to the vector of a word or token, each subsequently produced vector will add some additional value to that original vector such that they mean more and more specific things. Now, all of this is incorporated in a single head of attention. And this process happens about 10,000 times for a single pass of the network. And each attention block involves something around 100 different attention heads. And there's many different layers of attention. And these all happen in parallel, by the way. This might be too much for me to explain. So I'll just quote directly from the video to wrap things up. Where is it? Here it is. So each of the heads inside one of these multi-headed attention blocks has its own distinct key and query matrices, which are used to produce their own distinct attention patterns. And they have their own distinct value maps, which are producing their own distinct sequence of values, which again, you do this whole thing along the columns for. And every single output from those heads, which is a proposed change to make to the embedding that was in there, you add all of those up together to the original embedding that flowed in. So there's lots of different things that are potentially added onto it. And all of those distinct attention heads, which themselves involve all of these distinct patterns interacting with each other, make up an individual attention block. And so this process repeats itself in the process mentioned last week involving the attention block and multi-layer perceptron. And by the end, your hope is that it's not just the meaning of the original token, but rather whatever it needs to be able to predict what comes after. And I believe that's it from me. Thank you so much, and see you all next week.